As we look at all the alphabet soup of numbers and symbols, things that we're calculating in our least squares best fit line, it's important to go back and try to interpret and understand what it is that we're actually obtaining. And part of that is an analysis of the residuals, an understanding of the residuals. That you can make a lot of big picture mistakes by trying to use best fit lines that really aren't appropriate, and that appropriateness would be revealed by just examining these errors or the residuals that are left over from our model. And part of that is to clearly understand some of the assumptions that led to our particular model to begin with, and that is that these errors are uncorrelated random variables. Remember that our big picture model was that y was equal to beta naught plus beta 1x plus an error. Right? And so we had two random variables here, two unknown parameters and two unknown variables. X being 1, it's our explanatory variable, but it's a random variable, and then our error term is also a random variable. And from instance to instance, then the error is assumed to be uncorrelated random variable, and it has a mean of 0, and it was a constant in terms of its variance. So no matter what x was, our variance on our error term was the same. And we were also implicitly assuming that it was normally distributed as well. Right? Now, another important assumption is that we have somehow selected the order of the model correctly as a critical aspect. And by order, I'm thinking in terms of polynomials, right? A linear model is of order 1, a polynomial in more general terms, right? X squared would be order 2, etc., etc. That we have somehow selected an appropriate model to begin with, right? And again, we'll talk at another time about how we can make a polynomial kind of expression actually look like, in this case, a multiple linear regression model, but it'll still be a linear regression model if we handle it in an appropriate kind of way. Right, so this is important here, and another aspect of this notion is that it's a sort of a analogy between the analog world and the digital world, right? If you look at a analog camera, then you've got a different kind of continuity in the image that's created versus a digital camera. If you get down to a small enough little scale, you'll have nothing but bits, right? And so it's not a continuous kind of model. And so if you get down close enough, you can't really see the pattern. You have to step back. And the same thing can be true too when we think about an order of model. If I've got data that is n sets of data points, then I can always fit a polynomial of n minus 1 to that data, right? And it'll perfectly fit through that, every single one of those observed data points. But that doesn't mean it's the right model to be using, right? And so we have to think about all those sorts of things and in interpreting and using our model. And so this also sort of this digital age versus analog age, I can always take any sort of curve, and over small little segments I can approximate that with a linear model, and that might be appropriate. But when I go to the next segment, then if I don't update the linear model that I use, then I'm going to potentially have much larger error than if I would have just used a bigger picture model over the entire range. It would have increased my error in some ways, but you get different pieces depending on what it is that you're really doing there. Okay. The other aspect of looking at residuals and analyzing them is, first off, just to simply plot those. and see if there's any particular trends that emerge. And for the data that we had for the recharge and the discharge data, that you see that it bounces a little bit back and forth from other side is 0. We know that the sum of the residuals itself was 0, and so there is some sort of balance of the magnitude of the residuals. We see that for some reason we have an accelerated amount of, or large amount I should say, of air in this region from 14 to 15. And that might be worth exploring to try to understand here near the body of this data why we're getting this kind of thing. What's going on here that would sort of lead us to have that? Is there something about our difficulty in estimating the recharge there? Is there just natural variability at work? That sort of thing. And if you take a look at page 427 of your text, you'll see the same kind of thing of these errors plotted versus the data. And our ideal kind of world is about the same above, top and bottom, and a nice sort of even smattering of air top and bottom, right? Whereas here, where you see that you've got this sort of funnel that's created, that the air gets larger and larger the further we go out, suggests that there's something else potentially at work. Or down on this one you see that you've got this sort of U shape, and it often will either show up as U shape or an inverted U, and that's suggested that there's a nonlinear effect at work here that we're not capturing with this linear model. And so maybe we try a different kind of fit to the data then. And then this one is a double bow. It's really sort of a double funnel. Funnel opening up from the left, and then a funnel that opens up from the right as well. Are also suggestive of some other anomaly that's going on, or a linear model that maybe, well, in this case probably more of not so much a linear model, but something else happening to create this, and it makes you a little bit less comfortable about the linear model that you've created, and that maybe we might want to use a different version where we transform the variables of interest into something that might create the linear relationship. Okay, now that's all a subjective kind of view of the data. Let's get into some ways that we might look at this in a more numerical, quantitative kind of fashion. Now you might think we could histogram this data, although we don't tend to have enough data points oftentimes to make that a useful approach. So what we tend to do in these residual analyses are to go look at whether or not we really have a normal distribution. So you could do a normal probability plot associated with the residuals. That's one approach. And you could do a chi-squared goodness of fit kind of test as well. Another aspect of this is to perhaps standardize or normalize our error, because how large is the error? How do we know if that's large or small? And one way to do that is to standardize, call that standardized error d sub I, and we'll just take the e, the error, and divide by our standard deviation of our error, right, which this is really just S sub e. Okay, and keeping in mind that in a normal distribution, that say a z of plus or minus 1.96, remember on the normal curve, that would be associated with, that's nearly plus or minus 2 standard deviations, right? But we encountered that with the 95% confidence intervals. Right, so if we come along and we look at any errors that are outside of plus or minus 2 sigma, then that suggests to us that either we have an anomalous error value, or if we have a lot more than 5% outside of that something else is at work that's going on, right? And what it may be indicator of is if we look at residuals with a standardized, let's look at the absolute value of them, that are greater than 2, that residual may be an outlier. I say may because we know that there is a small probability that in just a natural variation that we might get something that's way out there. But if we get a lot of them out there, that says something to us that there's something else going on, as well as if we get just one single one that's way out there. And certainly if you go out to 3 standard deviations where 99.9% of the data should fall within 3 standard deviations, and we go outside of that, that really tells us something is quite rare and unusual that's happening. Doesn't, again, provide definitive conclusion, but it does give us some sort of suggestion that something else is at work. In fact, we'll be talking in another module about just that kind of notion when we talk about control charts and control limits that will be set out at +2 or +3 sigma from a mean. Okay, another way that we can look at these residuals is to calculate what's called the coefficient of determination. Now, for some reason, I don't know anybody that calls that the COD. They call it the coefficient of determination and write it all the way out. And probably because it gets confusing to say COV versus COD is hard to hear the difference. And that turns out to be the ratio of SSR over SST, where SSR is our regression sum of squares. And that turns out to be the total sum of squares minus the error sum of squares. Or sometimes from a calculation standpoint we'll just write that as 1 minus then SSE over SST. Now it turns out that the reason why you see an R squared here is because that turns out to be exactly equal to our sample correlation coefficient as well. So coefficient of determination is equal to the sample correlation coefficient squared, and that's why you saw on the Excel chart that they plotted or displayed the R squared value, right? And the R squared value, or the coefficient of determination, tells us how much of the variation in the response variable is explained by variation in the explanatory variable, right? So it tells us something about the leftover variability. That would be really this stuff right here, the leftover variability. Now, in terms of, let's go back and look at what these things mean and how this all kind of came about. Right? The error sum of squares is, of course, that's our symbol SS sub E, was the sum of our actual value minus the predicted value squared. Right? So the sum of the errors squared. Our regression sum of squares, SS sub R, are not to be confused with residuals, and it could be very easily confused. Right? That's the difference between our predicted value and the sample mean. Right? So that's the regression value, and there's your sample mean, just your pure raw sample mean for y. Right? And that's also equal to beta 1 times capital S sub xy. Right? And then we get the total corrected sum of squares. That's your SS sub t. That's the sum of the difference between your actual y's and the sample average. And that, by the way, is the same thing as capital S sub yy, or capital SR plus capital S sub E. Right? And that's also equal to beta hat S sub xy plus error sum of squares. So those are all important and crucial to keep in mind. Now, one last little part of this is to go back to some of our definitions to understand why did we use the word regression. And to do that, let's go back to our slope term, beta 1, can be shown to be equal to our correlation coefficient times our standard deviation of y over the standard deviation of x. And that means that our predicted value is equal to our sample mean plus r times sy over sx, sample standard deviations of each, the ratio of those two, times the x value minus its sample mean. Now what I've done here is I've substituted in for our beta naught value that it equaled y bar minus beta 1 times x bar. And since beta 1 was this, and it's capital R, so it'll go right like there. Right? So if our correlation is equal to 1, right, and let's let x equal the sample mean plus 1 standard deviation, then we find out that our predicted y value equals y bar plus s of y. Right, so if we have perfect correlation between x and y, right, so a straight line and the residuals will turn out to be 0, then our normal math that we learned, deterministic math, and we're 1 standard deviation away from the mean of x, is going to give us a y that's 1 standard deviation away from its mean. Okay, so deterministic math applies in our normal kind of way. But if r is equal to 0.5 and we still are letting x be 1 standard deviation away, we find out that our predicted value here, y hat, is equal to y bar plus 1/2 of our standard deviation. Right? And so what that tells us is that, in a sense, the line, the predicted value, is regressing us towards the mean. Right? That there's this other variation that's going on, but this relationship is regressing or pulling us closer to the mean. And that's why the word regress and regression has been used to describe this kind of analysis.